Very well. Now we have a few properties left to cover, and one of the properties, the last one, perhaps, or the last two, are the most important ones, and they are a little bit more complicated as compared to these first elementary properties. Before that, we have another sort of elementary property, which is property number 7, and that is known as the Parseval's relation. We have seen this property before from the Fourier series, and it said that the power or the energy, depending on what sort of a signal it is. For example, if it's a periodic signal, then that would correspond to the power of the signal. But if it's a finite duration signal, then you have to evaluate the energy. Whatever it is, power or energy, you can evaluate it in time domain, or you can evaluate it in the Fourier domain, and they will be equal. So for the Fourier transform case, it happens to be like this. The energy of our signal in time domain, which is this. For the power, the calculation is quite simple, similar. All you have to do is you have to evaluate the integral within one period, and you have to normalize by the period. 1 over t times integration within a period, absolute value x of t squared. That would correspond to the average power. This one is the energy, and they are the same square entities. This evaluation is equivalent to the same evaluation in the Fourier domain, from minus infinity to infinity, d omega. So, whichever is easier for you to evaluate, when I ask you to evaluate the energy of the signal, you have to evaluate the integrals in either way. For example, this is the most typical example. Suppose that I give you a sinc shape. Suppose it's a time domain signal, sinc shape, and I ask you what is the energy of that signal. When you take the square of a sinc square, it will be sine square of t divided by t squared, and then you have to take the integral as an absolute value with a square. Well, that integral will be a headache, clearly. So what is a better idea to do it, to approach the problem? Take the Fourier transform of that. And that Fourier transform can be evaluated from duality. The sinc's Fourier transform is a rectangular shape. Now what is the square of a rectangular shape? It's the same square. If the value is a, the peak for the rectangle is a, now it will become a square, whatever that value is. But it is still going to be a rectangle, and if you integrate that rectangle, the square of that rectangle, it will be just an area of a rectangle. So it's very easy to evaluate the energy for a rectangular shape. It may be quite easy for triangular shapes, etc., or for impulses even. But if you have if you have such complicated time or frequency domain signals, whichever I may ask you, you have to first go to the other domain, which is a simpler shape, and then in that simpler shape you evaluate this square integral. That is the methodology, because they will correspond to the same energy or the power. Alright? That's how you need to do it. Now, I will open a new page for the last two, because they are important, as I say. The first property, let's say 8th property, is convolution property. We have been using it in Fourier series again, but in Fourier transform it's a more general way of putting things. What we really say is the following. If you have z of t is equal to x of t convolution with y of t, And we we perform convolution usually in linear systems, right? System response is h of t, impulse response, and we convolve our input x of t with h of t to produce y of t. Now, if you know how to take the Fourier transforms, then we already have the formula saying that if you have the Fourier transform of x of t as x of j omega and y of t as y of j omega, then the Fourier transform of their convolution, which is, z of j omega, is equal to x of j omega times y of j omega, as simple as that. You just multiply. And we were applying this property in the Fourier series as follows. What were we saying? We were saying that we have an input x of t which is periodic and it has Fourier series coefficients ak's. And then h of t has a Fourier transform h of j omega, and I was calling it h of omega, which was the frequency response of our system. It can be a low pass filter, high pass filter, etc. There was even an exam question related to that. So, in order to evaluate the Fourier series coefficients of the output, what were we doing? Do you remember? We were doing like, we were saying that BKs were equal to AK times H of omega at omega is equal to K times omega 0. So, this AK is in fact like the Fourier transform with the corresponding frequency omega is equal to k times omega 0. So we were multiplying x of k times omega 0 and h of k times omega 0 to find y of k times omega 0. And since the frequency separations were discrete in the Fourier series, we don't have all the omegas, we only have k times omega 0 versions. 0 times omega 0. Omega 0, 2 omega 0, 3 omega 0, etc. And we were making this multiplication only at those certain points, discrete sample points. But now, we have a more general formalism. We say that we can multiply the Fourier transform or frequency counterparts at each and every omega. So this formula for the multiplication in frequency domain is valid for all omega, not only k times omega 0 points. It's valid everywhere. So filtering in time domain is a convolution, in frequency domain it's a multiplication. And those multiplications mean a lot of things. For example, if h of j omega is a low pass filter and x of j omega is the Fourier transform of our signal, which can be, I don't know, like, okay, suppose that it's like this. And the time domain corresponds to 2 over 1 plus t squared. So the time signal was 2 over 1 plus t squared was x of t, and h of t was a sinc. And I want you to find the output, which is y of t. And how do you do that in time domain? You have to convolve this altered signal with the other altered sinc signal, and that convolution would be a headache. It's even impossible, I guess. But in the Fourier domain, the picture is clear. It's going to be something like this. This will be y of j omega. At least you know the Fourier transform of that, and it looks quite simple. It's just the multiplication of the two top shapes. The top shape forces all the frequencies out of a certain range of the width of the rectangle to become 0, and in between it keeps the original shape. So that's low-pass filtering, basically, and things are very easy in the Fourier domain as compared to the time domain. From the duality, now, you may guess that the opposite is also true. If things are complicated in frequency domain, just convert everything into time domain and apply the convolution there. It may be simpler. But filtering is multiplication in frequency. So let's write it. Filtering is equivalent to multiplication in frequency domain. That is our important, extremely important property of observation. There are some proofs. There are like 4 distinct ways of proving this property. I find one of them quite simple. So let me try to show you a proof of that. By the way, this proof is not very nice way of proving it in the concept of rigorous proofs, because it requires some extra information to attach into the problem. It's like this: if x of t, but it's neat. If x of t passes through h of t, the output is y of t. We know, right? And now let me write this x of t as the inverse Fourier transform. This is x of t, you see? Goes in. Now what is the output? The output requires the knowledge of one thing that we have seen before, previously seen before. Now, if only this thing, e to the j omega t, comes into h of t, what was the output? Do you remember that? The output would be, in other words, do you remember this? Do you remember the output? The output was h of omega times e to the j omega t. That is, if the complex exponential comes into the system, the same complex exponential goes out from Fourier series. We remember that. That's why we were multiplying the both sides with the Fourier series coefficients and say that if a times e to the j omega t comes in, then a times h of omega times e to the j omega t goes out. That's why bk is equal to h omega times ak. Okay, so here we have h of omega e to the j omega t. Then I didn't say that this h of omega is the Fourier transform of h of t. I didn't say it, but it's like the frequency way of representing things, I said. But now we know it already. This is not h of omega, but it's h of j omega e to the j omega t. So just remember this. And in the previous expression here, therefore, this e to the j omega t will be transformed into h of j omega times e to the j omega t at the right hand side. And all the others are independent from t. It's just an integration of combined lots of e to the j omega t's within this integral, and these are just scales independent from t. 1 over 2 pi is independent from t. And the output will be like this: 1 over 2 pi integral from minus infinity to infinity x of j omega h of j omega e to the j omega t dt. What am I doing? dt. Oops. Like this. And now, do you see that this thing must be equal to y of t. So y of t is equal to 1 over 2 pi integral x j omega h j omega e to the j omega t. And y of t, the inverse Fourier transform of that, is equal to 1 over 2 pi from minus infinity to infinity y of j omega e to the j omega t d omega. By the way, I'm sorry to write dt's all around here. They must be d omega. Excuse me about this. D omega, because they are the inverse Fourier transform. Sorry, I just made an error there. So now the new expression here and this expression are the same. They correspond to the same thing. And from there, what you see is this y of j omega is equal to x of j omega times h of j omega. So they are equal to each other, which is a proof, right? It is saying that if you convolve x and h to make y of t, then you must multiply x of j omega and h of j omega to find y of j omega. That's one alternative way of proving things. Proving this property. But the property itself is perhaps more important than the proof. It's just a way of motivating how you can prove something. The property is very significant, and you will have to apply it quite often in your exam, not only examinations, but in your engineering life probably. Whenever you need to filter out something and find the output of a system, the first thing that you have to, or you will be attacking is like this. Is the system linear and time invariant? First, let's check it. If it is linear and time invariant, okay, let's forget about convolving in time then. Let's forget about it. Let's take the Fourier transform of the impulse response to find the frequency response of the system, h of j omega. And then I will take the Fourier transform of my input to find x of j omega. Their multiplication is way simpler than the convolution itself. I will just multiply them to find the Fourier transform of the output. So at the output, how do I proceed to find the time domain signal? Well, since you have yj omega, you can take the inverse Fourier transform to get back to y of t, which is the output. Now, there are some side properties of system responses. As you may remember, if you have x of t going into h1 of t and its output is going into h2 of t to make y of t, we said that y of t is equal to h1 of t convolution h2 of t convolution x of t. And since convolution itself is a linear operator, it doesn't really matter which two things you convolve first. You can even interchange their places. And in frequency domain, the situation is quite similar. Y of j omega is equal to h1 of j omega times h2 of j omega times x of j omega. Since it's a multiplication, it doesn't matter which of the two terms you multiply first. Multiplication will clearly be the same. Now, let's see an example whose answer we already know, but let's now try to think of it in a different perspective, in a different linear and time invariant system perspective. First of all, do you remember this property? It was even a property. If x of t has a Fourier transform of x of j omega, what was the Fourier transform of this? X of t minus t0. e to the minus j omega t0 x j omega. It was this. Remember that? Now I'm telling you that this x of t minus t0 can be achieved like this with a system. It's just a delay system. X of t goes into a system h of t, and the output is y of t is equal to x of t minus t0. Can you guess by inspection only the impulse response h of t? What is the impulse response of a delay system? It has nothing to do with x, of course, because it's just a delay system. Consider one signal h of t with which, when you convolve with x of t, the output will be x of t minus t0. How do you obtain x of t minus t0? What is the thing that you have to convolve x of t with? Yes? Yes, it's an impulse at t0, which is delta t minus t0. H of t must be equal to delta t minus t0. Exactly. So when you convolve x of t with delta t minus t0, what is the output? It is x of t minus t0. Okay? It just applies a shift. Now, what is the Fourier transform of x of t? Of course, it's x of j omega. Now the problem is, what is the Fourier transform of h of t? What is h of j omega? It's the Fourier transform of delta t minus t0, and that is e to the minus j omega t0. And the Fourier transform of y of t is y of j omega. And from the multiplication versus convolution property, we know that if you are convolving x of t with h of t to get y of t, then you have to multiply x of j omega and h of j omega to get y of j omega. So y of j omega is equal to x of j omega times e to the minus j omega t0, and well, it's here anyway, isn't it? The Fourier transform of the shifted signal is also e to the minus j omega t0 times x of j omega. So they are the same. You can think of it like this as well. Even the simplest delay or shifting system is a system which has a frequency response, and the frequency response is the Fourier transform of h of t, which is the Fourier transform of delta t minus t0, and that is e to the minus j omega t0. So when you multiply them with x of j omega, you will get the output Fourier transform. Again, sometimes very simple concepts like these ones are confusing because it's too simple. Okay, it's like showing the right ear with your right hand and then rotating twice and trying to hold it again. But it's just for the sake of illustrating their equalities. Yeah, okay. Now this one is a good one. We know that the derivative of a signal will make the Fourier transform to be multiplied by j omega in the Fourier domain. It was the property that we saw last hour. Now, what we can say is then something like this. If x of t comes into a system which takes the derivative, the time derivative, whatever the impulse response of that kind of a system may be, by the way, the impulse response of this derivative taking system is quite complicated. It's an infinite extent impulse response. Not a compact or short way of representing, but whatever this system's impulse response is, we don't know it, but we know that its Fourier transform h of j omega is equal to j omega, because it is multiplying our x of j omega, multiplying our x of j omega by j omega. So that's the way the filter behaves. It's a filter. It's a linear and time invariant filter, and in the Fourier domain, it is multiplying our Fourier transform by j omega. So that j omega must be the Fourier transform of the impulse response of the system. So what is the time domain counterpart? What is h of t then? God knows. For that, you have to take the inverse Fourier transform formula and try to get some tangible h of t. I don't recommend it, but you can do it, at least theoretically. That would be a very hard operation. The impulse response doesn't make much sense here. The Fourier domain is better visualizing it. And by the way, is it a high-pass filter, a low-pass filter, a band-pass filter, whatever? What would you say about the frequency characteristics of this filter? If you want to give a name, something pass, something stop filter, or things like that, what name will you give for this? Is it all pass really? Is it passing all the frequencies? There is a problem at omega is equal to 0. It doesn't pass the DC. At omega is equal to 0, j omega is also 0. So our Fourier transform expression is multiplied by 0. It doesn't pass the DC. It's not all pass. It's not passing DC. It is attenuating all the small frequencies because it's multiplying by omega. So the small frequencies are multiplied by smaller numbers, but larger frequencies are multiplied by larger numbers. So high frequencies are amplified. It is some sort of a high-pass filter. And can you, in time domain, guess that taking the derivative is a high-pass operation? Because it only detects changes. If something is flat, then the derivative will not produce some large numbers. But if something changes, then the derivatives will exhibit peaks. In image processing, it's like detecting the edges, the boundaries, only the changes. So when you take a derivative, you detect changes, you detect edges. And that is a very high pass thing. You don't pass the low variations, you only pass the high variations, the high frequency things. The variation, if there is a change in the signal, that variation corresponds to a high frequency. The more variation, the more abrupt variations you have, the higher frequency it is. Frequency and variations have a strong relation in that way. So that's why a derivative system is a high-pass filter, and we can also see it, we can also observe it from the Fourier domain version of the same thing. Okay. Now, do we have any other example? Well, of course, you can think of any examples. The number of examples for this property is infinitely many. You can think of all the possible signals which have a relatively easy way of evaluating the Fourier transform. And when I ask the convolution of them, you just need to take one by one the Fourier transforms of each and multiply them in the Fourier domain. That's the way you do. But from the duality, we must proceed with the final property using the duality property and the convolution versus multiplication. You see, if you convolve in time domain, you have to multiply in frequency domain. But there's also duality. And it says the following. If you multiply in time, if you multiply two things in time, then their Fourier transform correspondence would be the convolution of their Fourier transforms on the omega axis. How do you convolve on the omega axis? You flip around one of the functions and then slide. take the overlaps, take the integrals of the overlaps, etc. We know how to convolve, right? So that new, the name of our new property is multiplication in time. And from the duality, the situation is as follows. If you have z of t is equal to x of t times y of t, then the Fourier transforms will behave like this. Capital Z j omega will be equal to 1 over 2 pi, that's a scale coming from the duality, x of j omega convolution with y of j omega. So you have to apply the convolution this time in the Fourier domain. And there is one significant application of this thing, that is telecommunications. In telecommunications, there is a concept of so-called modulation. Did any of you have any ideas about modulation and telecommunications? Okay, modulation, then I have to explain, is carrying our baseband signal, for example my speech or any music, which is low frequency, baseband they say, to a very high frequency range. For example, megahertz, kilohertz, whatever, terahertz, even gigahertz range, so that they can be transmitted to long distances, because that's the way the waves behave in atmosphere and even in the space. They cannot penetrate to long distances. Baseband signals cannot go to kilometers away. No matter how much I may shout, if you are like 20 kilometers away, you will not be able to hear me. But the propagation of higher frequencies will be at longer distances. And by the way, the others will not be able to hear you. That's a nice side effect, because when I shout, everyone will listen. But when I transmit at a high frequency, others will not notice if they don't know at which frequency I'm transmitting. The only guys who will receive my message will be the ones who had a receiver, radio, which is called demodulation. So I'm modulating to high frequency, and your radio is demodulating back to the baseband so that you can hear. But the whole phenomenon of this so-called modulation is somehow, there are technical differences of course, similar to this. You are saying that your x of t is your message, which is baseband, and y of t is called a carrier, which is a high frequency sinusoid. A typical example of this y of t is cosine omega c t. Omega c is the carrier frequency, like 100 megahertz. 100 megahertz times 2 pi. Of course, this is in the omega domain. If it's in the f domain, it will be 2 pi times fc times t. Fc will be the carrier frequency. This is the carrier frequency in radians per second, not hertz or kilohertz. So you are multiplying your x of t with a cosine omega ct. This is a multiplication in time domain. And how come it performs a modulation? That is from the property, which is a convolution in frequency domain. What happens if we convolve the Fourier transforms of the two signals? The Fourier transform of x of t is x of j omega. The Fourier transform of cosine is, do you remember what the Fourier transform? Huh? No. Remember, this is a periodic signal, cosine. So it has two Fourier series coefficients. What were the Fourier series coefficients? 1 over 2 and 1 over 2. So what's the Fourier transform? Two impulses corresponding to those places. multiplied by 2 pi. 2 pi times 1 over 2 is pi. So an impulse with a magnitude of pi at frequency omega c. And another one is another impulse with the same magnitude pi at minus omega c. And the way to represent it is this. The first one is an impulse with magnitude pi at omega c. The second one is another impulse at minus omega c with the same magnitude of pi. This is the Fourier transform of cosine omega ct. Okay. Now I need to convolve them and divide by 1 over 2 pi or multiply by 1 over 2 pi to say that this is the Fourier transform of my input. So there is a 1 over 2 pi term here, and there is a pi term for the impulses. When they cancel, only 1 over 2's will come into the picture, and it will be 1 over 2 x of j omega convolution with impulse at omega c and impulse at minus omega c. So I need to perform this convolution. Again, let's think of a convolution with an impulse. What does it mean? How do we convolve with an impulse? We just carry our Fourier transform or our signal to the position of the impulse. You remember that? We shift our signal by the amount of the position of the impulse. So will you all agree with me when I write that this convolution would be nothing but x of j omega minus omega c plus x of j omega plus omega c. So by convolving with two impulses, I had two replicas of my x of j omega. One shifted to omega c, the other one shifted to minus omega c. And that's the whole point. When you shift your baseband Fourier transform shape to omega c and to minus omega c, it means it's not baseband anymore. It must be now around omega c and minus omega c, which are very high frequency. Now let's see what's happening, for example, in the as a graphical illustration. The situation is as follows. You had, let's assume that you had a Fourier transform x of j omega, which is baseband, let's assume. So it is between ws and minus ws. That's the bandwidth of our baseband signal on the frequency axis. Okay. It's just an illustration. It doesn't have to be like this, of course. Your message it can be quite different. But this is just a low-pass baseband signal. Omega ws, for example, is like 20 kilohertz, like the highest audible range that I can produce as the voice. Now I need to convolve them with the carrier. What was the name that I gave to carrier? Y of j omega. Let's assume that these are two impulses at omega c, carrier frequency, and minus omega c, and their magnitudes were pi and pi. Let's assume the peak here is A. So when we convolve the top shape with the bottom two impulses and divide by 2 pi, of course we have to multiply by 1 over 2 pi, what's going to happen? The triangular shape, the baseband triangular shape, will move to around omega c, and it will move to around minus omega c. And it will be like this. what will be the peak? Pi times a divided by 2 pi. It will be a over 2. So I'm drawing now z of j omega, which is this shape. So my original triangular shape has moved to around omega c and minus omega c, which are high frequency. This minus thing, don't think about it as a physical entity. Okay? It's just the conjugation. It just comes from the conjugation property, the mathematical property. Therefore, the whole thing is at omega c, or around omega c only. Think of this part as the physical thing. The other one is just a mathematical conjugate. So my original signal was a baseband signal. Now my signal is this, which is high frequency, and it can go long distances. That is called modulation, if omega c is a high frequency. So it can go long distances. But how about the radio? How will the radio receive this? How will it push it back to, or pull it back to around DC? Can you think of a methodology to make these triangles to come back to the origin, to make it baseband again? By the way, if we put some legends, this is omega c minus ws, this is omega c plus ws, etc. So that's the same bandwidth that goes at high frequencies. How are we going to demodulate? How does the radio work? We have to pull it back to around the origin. Can you think of a method? No, delays will not change the frequency. Delay is applying a phase only. No. That's not something that we can do. What you need to do is reconstruct it. No, if you apply a low pass, nothing passes in the origin. Band pass, okay, that's good, but it's not the same as the top. I want to have this, because that is the thing that I can hear. If I pass these through band pass, I will not be able to hear. I will not be able to hear this one either. That's why you cannot hear anything right now, because it's in the air and you have to demodulate. That's the method that I'm asking, to bring it back to zero. The reconstructed signal I'm calling R of t is, the demodulation radio is cosine omega ct, again multiplying our previously multiplied signal c of t, and then some low pass filtering, of course. Can you see it in time domain? Can we see it in time domain? That is equal to cosine omega ct times z of t is already cosine omega ct times x of t, isn't it? Cosine theta times cosine theta, what is the expansion of that? It is 1 minus, say? I don't mind. 1 minus sine square omega ct, okay, times x of t, which is x of t minus x of t times sine square omega ct. Now this thing is x of t that you can hear. The other one is a modulated waveform which you cannot hear anymore. So you can just apply a low pass filter now, and that will get rid of that term, and you will get back to x of t. Now, does it work in Fourier domain is our issue. It's not the trigonometric identities that I'm looking for right now. So how come it works in the Fourier domain? So z of j omega was like this. I'm going to draw it a little bit smaller. Now if I multiply in time domain with the same cosines, which is again y of j omega, let's say, on the axis of omega. If we multiply in time domain, we need to convolve those triangles with these new impulses. And how are we going to do that? I will show it on the board. For this, for convolution with this impulse, you need to take this and shift it towards right by an amount of this. So shift it and put it here. For convolution of the whole thing with the left hand side, you need to shift this one to the left side by an amount of this and put it here. That's what I'm going to do. So if I shift the top shapes to the right by omega c, I will get this triangle and the triangle at 2 omega c. This is around 0, which is the shifted version of the top shape towards right by an amount of omega c. And then with red this time, I will draw the shifted version of the top shape towards left, which is this triangle and another triangle around minus 2 omega c. Okay, do we agree? Now we are left with one thing. We need to combine, add the red and the black shapes, which are identical in the center. The red and the black triangles are identical in the center. When we combine them, we will just have twice the triangle, another triangle here and another triangle here. Now by applying a low pass filter, we can get rid of these very high frequency components, and we will have only one triangle in the center, which is the same shape as the shape that we started with at the top. So that is how modulation and demodulation works. We multiply with a cosine to modulate, to split to two frequencies, and then we multiply again with another cosine, which would make replicas of these and these, and in the center those two will merge, which will make the original waveform in the Fourier domain. And that is R of j omega, and I say that it is a constant times the same as original x of j omega. That constant, it's not important. You can always volume up your radius. It increase or decrease the volume, it's just a scale. It doesn't change the waveform. So that's how modulation and demodulation briefly works in telecommunications. So in the next semester, when you encounter these things, which you will encounter, you will have to say that you already know it. You already know how to do it. You multiply in time domain, which means you convolve in frequency domain with two impulses corresponding to the carrier. That is modulation. Okay, now we can stop at this point. We will continue next week.